A basic principle of physical engineering states that drawing an intended path on a blueprint is merely the beginning of the job. The real achievement is protecting that path from the disorder of reality. An electrical circuit must survive extreme physical pressures: heat, material fatigue, friction, and vibration. The engineering goal is to ensure that the intended function remains intact after the design is placed inside a hostile environment. This exact distinction applies directly to the design of artificial intelligence. Modern models excel at generating a sequence of steps, writing coherent arguments, and producing fluent text. Yet, producing an output does not mean the reasoning path itself was controlled. An unmonitored model can satisfy all local requirements and preserve the appearance of logical reasoning, while silently replacing the original objective with a different problem that is easier to solve. This reveals a gap between a system's ability to generate a sequence of steps and its ability to protect the original intention behind those steps. The industry relies heavily on two mechanisms: producing a path, generating sequential steps, and verifying an output, checking if a final step meets basic criteria, like safety or factual accuracy. Both methods fail to track the thousands of intermediate decisions, assumptions, and reallocations of attention an LLM makes during long-horizon tasks. This diagram illustrates the necessary alternative: path governance. Rather than freezing a single predetermined route, path governance is the dynamic regulation of how candidate routes are generated, compared, pruned, and revised in real time. This architectural approach operates under what we call the energetic framework, which treats reasoning as a structured movement through a field of constraints and costs. To build trustworthy, long-horizon AI systems, we must stop evaluating isolated final answers and start architecting the structural movement of reasoning itself. When an AI loses track of its original goal, it does not drift randomly. The trajectory is distorted by predictable, recurring pressures inherent to the architecture of the model itself. We can see the first of these structural forces in this visualization: probability attraction. Language models naturally gravitate towards statistically familiar continuations, often abandoning difficult, novel discoveries for solutions with lower generative resistance. The second force is local plausibility. A sequence can be composed of individually correct, reasonable steps that collectively walk the system away from the global destination. The third force is closure pressure. Generative systems are strongly oriented toward completion, prematurely compressing uncertainty into false confidence to force a definitive answer before the evidence justifies it. Combined, these three forces ensure that a model operating without an explicit control structure will consistently seek the path of least resistance. Highly capable models left unchecked will seamlessly and eloquently execute the wrong task. When tasks extend over a longer time horizon, a new set of environmental distorters emerges. This graphic demonstrates the fourth force: contextual drift. In extended tasks, the system begins optimizing for the most recent local prompt, confusing recency with relevance, and abandoning the priority structure of the whole task. The fifth force is metric substitution. When genuine success is difficult to evaluate, systems adopt easily measurable proxies. They will swap a rigorous scientific explanation for a simple literature summary, performing well against the proxy while failing the original objective. The sixth force is resource pressure. Finite limits on attention and computation force the system to favor routes that are shorter and cheaper to justify. Without a structural defense against these forces, efficiency and local context will silently replace truth and accuracy. The standard industry response to these drift forces is to insert an automated verification algorithm and a human reviewer at the very end of the process. Automated verification, as shown in this diagram, usually asks bounded questions. It checks if the code runs or the inference is valid locally. A verifier acts as a checkpoint, flashing green for local accuracy while remaining blind to the fact that the system is elegantly solving the wrong global problem. The human-in-the-loop paradigm suffers a similar failure when confronted with complex intermediate drift. Human reviewers are vulnerable to the same surface effects that make model outputs persuasive. They cannot manually inspect thousands of invisible micro-decisions, and they are easily fooled by fluent, professionally formatted text that conceals an invalid reasoning route. human intent must be mechanically embedded into the architecture of choice during execution. Relying solely on terminal approval creates an illusion of control. To counter this physics of drift, the energetic framework deploys a series of 6 governance functions. Function 1 is preserving goal identity. A goal cannot exist as static metadata attached to a prompt. It must remain an active, multifaceted identity that dictates the conditions of successful completion and acceptable posts throughout the entire run. Take a medical scenario like the one shown here. The identity of the goal, treat cancer, involves minimizing toxicity and extending survival. If an AI optimizes solely for short-term tumor shrinkage at the expense of healthy tissue, it has satisfied a local indicator but suffered goal drift. Function 2 is keeping constraints active. A constraint must possess causal veto power over attractive paths. If a system can remember a rule linguistically but still violate it during generation, that constraint lacks causal force. Function 3 is regulating candidate competition. The system must structurally manage the tension between exploring new routes and committing computational resources to the path with the highest potential for valid advancement. These first 3 functions establish a foundation where human priorities physically constrain the system's internal mathematical decisions at every single step. Function 4 is detecting drift. The system must persist in referencing the global goal, repeatedly evaluating whether a correct local step has subtly altered the overall direction of the task. Function 5 is structured backtracking. When a path fails, a reasoning system cannot blindly retry. It must extract structural data about which assumptions were falsified and use that evidence to reconfigure the next search space. Function 6 is distinguishing output from completion. Looking at this flowchart, we see that generating a text document is merely an output. Language generation serves as an intermediate stage of the process, used to orchestrate real-world execution. Under the energetic framework, language generation is demoted from the status of a final objective to that of a tool for measurable state transitions. Consider 2 identical AI outputs that arrive at the exact same correct answer. Here is the structural difference. The output on the left was reached through a chaotic path pulled by statistical coincidence and lowest resistance generation. The output on the right was reached through a governed structure, active constraints, verifiable state transitions, evidence testing, and disciplined backtracking. This highlights the ultimate objective of path governance: causal continuity. The first correct answer is an accidental hit. The second is a reproducible, reliable capability, the exact kind of capability required to operate autonomous, long-horizon AI systems in complex environments. AI engineering does not end when a prompt is designed. It succeeds when the reasoning path remains faithful to its original purpose under the continuous, distorting pressures of reality.